Welcome to this guided lesson on architecting data in Python. In this video, we are going to move from the simplest built-in containers to the larger structures engineers use when data starts to behave like a system: stacks, queues, linked lists, trees, and graphs. The point is not to memorize a vocabulary list. The point is to learn how to choose the right shape for the job. Every Python program has a hidden architecture. Even a short script has to decide whether data should be ordered, mutable, unique, searchable, hierarchical, or networked. When those decisions are casual, the code may still run, but it becomes harder to reason about. When those decisions are intentional, the program becomes easier to change, faster to search, and clearer to debug. The first distinction is between built-in structures and user-defined structures. Python gives us lists, tuples, dictionaries, and sets as immediate materials. They are like the standard beams, brackets, and joints in a workshop. They are familiar, optimized, and available without ceremony. On top of those materials, we can build custom structures such as stacks, queues, trees, graphs, and linked lists. Those are not magic. They are design patterns made from the built-in pieces. That is the engineering mindset for this deck. You do not start by asking, which data structure sounds impressive? You start by asking, what does the data need to do? Does it need to preserve order? Does it need to change over time? Do you need to find an item instantly? Are duplicates meaningful or distracting? Does the data branch like a hierarchy, or does it connect like a network? Let us begin with lists. A list is Python's default dynamic, ordered sequence. If you need to keep items in insertion order and you expect the collection to grow, shrink, or be rearranged, a list is usually the first tool to reach for. Lists are mutable, which means you can append to them, insert into them, remove from them, and update individual positions. That flexibility is the list's strength. It is also the reason lists should be used deliberately. A list is excellent when order matters and the data is expected to change. It is less ideal when every element must be unique, when lookup by key is the main operation, or when the data should never be modified. Lists are great working surfaces, but not every problem wants a working surface. Tuples are the contrast. A tuple is an ordered sequence, but it is immutable. Once created, its contents are sealed. That makes tuples useful for fixed records, coordinates, configuration pairs, and values that should travel through a program without being accidentally changed. A tuple is not just a list with different punctuation. It is a signal that the data represents a stable block. This can be especially useful in APIs and internal program design. If a function returns a point, a date range, or a small fixed grouping of values, a tuple can communicate that the shape is stable. Because tuples are immutable, Python can optimize them in ways that often make them lighter and faster to iterate than lists. The deeper lesson is that immutability is not only a safety feature. It is a design message. Next are dictionaries, one of the most important structures in Python. A dictionary maps keys to values, which makes it the natural choice for fast retrieval. If you know the key, you can get the value directly instead of scanning through a sequence. In practical terms, dictionaries are the structure you reach for when the question is, given this identifier, what do I know about it? That pattern shows up everywhere: user IDs to profiles, symbols to prices, names to configuration objects, routes to handlers, and labels to computed results. Dictionaries are mutable and, in modern Python, preserve insertion order. But their central purpose is not sequence. Their central purpose is relationship. A dictionary says that one piece of data names, indexes, or points to another. Sets solve a different class of problem. A set stores unique elements. If duplicates do not matter, or if duplicates actively get in the way, a set is often the cleanest tool. Sets are especially useful for membership checks, removing duplicates, and computing relationships between groups, union, intersection, and difference. Think about tags, permissions, seen items, available features, or IDs that have already been processed. If the program keeps asking, "Have I seen this before?" or "What overlaps between these two groups?" then a set usually expresses the intent better than a list. You could do the work with a list, but the code would be less direct and often slower. The diagnostic matrix brings the built-ins together. Lists are ordered and mutable, but not unique. Tuples are ordered and immutable. Dictionaries map keys to values and are built for fast lookup. Sets are unique and optimized for membership. When you know those trade-offs, you can often choose the right built-in structure before reaching for anything custom. Now we move into custom architectures. These are built from the raw materials, but they enforce stronger rules. A stack is a last-in, first-out structure. The most recent item added is the first item removed. That is exactly what you want for undo history, backtracking, depth-first search, browser navigation, and temporary state where the newest action should be reversed first. In Python, a simple stack can often be implemented with a list using append and pop. The important thing is not the container itself. The important thing is the rule: push onto the stack, pop from the stack, and only interact with the top. When the rule is clear, the workflow is predictable. Queues are the counterpart. A queue is first in, first out. The first item that enters is the first item that leaves. That makes queues natural for task scheduling, breadth-first search, request handling, and pipelines where fairness or chronological order matters. Python's collections module gives us deque, which is efficient for adding and removing items from both ends. The mental model is simple. A stack asks, "What was the most recent thing?" A queue asks, "What has been waiting the longest?" Those two questions lead to very different program behavior. If you mix them up, an algorithm can still run, but it may explore the wrong path or process work in the wrong order. Linked lists are another step away from Python's built-ins. In a linked list, each element is a node, and each node points to the next node. The data is not stored as one contiguous sequence in the same way a Python list abstracts it. Instead, movement through the structure depends on following pointers. In everyday Python, linked lists are less common than in lower-level languages, because Python lists are already powerful and convenient. But linked lists are still worth understanding because they teach an important idea: data can define its own navigation. Each node carries not only a value, but a relationship to the next place to go. Trees organize data into strict, nonlinear hierarchies. A tree starts at a root and branches downward. File systems, HTML documents, organization charts, parsed expressions, and decision structures all fit this pattern. Trees are useful when every item has a parent-child relationship and there is a clear direction from root to branch to leaf. When you model data as a tree, you are saying that hierarchy matters. The structure gives you paths, levels, subtrees, and terminal nodes. That makes trees a good fit for recursive algorithms and for data that naturally decomposes into nested parts. Graphs are more general. A graph is made of nodes and edges, and the relationships can be many-to-many, circular, weighted, directional, or undirected. Graphs show up in social networks, dependency maps, routing systems, recommendation engines, fraud detection, and knowledge graphs. If trees are hierarchies, graphs are networks. Graphs are powerful because they let us model complex relationships without forcing them into a single parent-child chain. But that freedom comes with responsibility. Graph algorithms can be more complex, and graph data can become harder to inspect casually. Use a graph when the relationships genuinely require network thinking. The final slide gives us the decision tree, and this is the part to remember. First, ask whether the data is hierarchical. If yes, think tree. If it is networked or cyclical, think graph. If the main operation is lookup by key, think dictionary. If uniqueness or membership is the priority, think set. If the workflow is last in, first out, think stack. If it is first in, first out, think queue. If it is simply an ordered mutable sequence, think list. If it is a fixed ordered record, think tuple. That decision process is the heart of data architecture in Python. The language gives you simple tools, but professional code comes from choosing them with intent. A good data structure does not just hold values. It expresses the rules of the problem. It makes the next operation obvious. It reduces accidental complexity. So as you design Python systems, pause before reaching for the nearest container. Ask what the data needs to preserve, prevent, expose, or accelerate. The answer will usually point toward the right shape. And once the shape is right, the code around it becomes calmer, clearer, and easier to trust.